Let us begin this collection of exercises on level curves with a recap of the definition of what level curves are. Given a function f defined in a domain of the Cartesian plane and with values in R, that is a real function of two real variables, a level curve of f at level C is the set of points of D such that fxy is equal to C. We point out the fact that the level curve must be a subset of D. In the basic exercises on two variables functions we are interested in, level curves can be points, straight lines, conics, or graphs of one variable functions. All, we repeat, these curves must be intersected with the domain of the function. For center value of C, the level curves can be empty. Consider the function fxy equals 1 plus xy over x squared. The domain of this function is x different from 0. This condition comes from the denominator, that is all the Cartesian plane except the y-axis. The level curves are defined by the equation 1 plus xy over x squared equals c. This can be rewritten in this way: y equals cx squared minus 1 over x with x different from 0. In order to know the characteristics of these level curves, we need a quick study of the properties of the function gc. We begin with the limits as x tends to plus under minus infinity. When c is 0, both limits are 0. When c is positive, the first limit is plus infinity, the second is minus infinity. When c is negative, the first is minus infinity, the second is plus infinity. The limits as x tends to 0 from the right and the left are minus over plus infinity, precisely minus infinity from the right, plus infinity from the left. The first derivative is this, and if c is positive, the first derivative is always strictly positive, so the function is increasing in minus infinity 0 and in 0 plus infinity separately, not in all the real line. If c is negative, we have two roots here, plus or minus 1 over square root of minus c. The function is strictly decreasing, then increasing, then again increasing, and then again decreasing. So we have a local minimizer in the first root of the first derivative equals 0, and a local maximizer in the second root. The following picture illustrates the behavior of these level curves for the 5 different values of c. C equals 0, the red, c equals 1, the blue, c equals 2, the cyan, c equals minus 1, the green, and here we have a minimum here and the maximum here, c equals minus 2, the magenta, and also here we have a minimum and a maximum. Consider now the function square root of x squared over y plus 1. For the domain, we must split the problem in two parts. If x squared is 0, we have only the condition y plus 1 different from 0, and this is the second part. If x is different from 0, we need y plus 1 strictly positive in order to have a positive radical. The level curves are defined by this equation. No solution if c is negative, because the square root is always positive order 0. If c is 0, we have exactly x equals 0 with the condition y different from minus 1. If c is positive, we square both members and we obtain this expression always with the condition x different from 0. So the level curves are simply obtained with these conditions. When c is 0, it is the vertical axis except this point. When c is different from 0 but positive, we have parabolas always without the vertex that is excluded because it belongs to the line y plus 1 equals 0. Consider now the function x squared over y minus 2x squared. The domain is given by the condition y minus 2x squared different from 0 coming from the denominator. That is all points of the Cartesian plane except the parabola y equals 2x squared. The level curves are defined by the usual equation. So if c is 0, we obtain x squared equals 0. If c is different from 0, we can rewrite this equation in this way. Then, for c equals 0, the level curve is the y-axis, that is x equals 0, without the origin that belongs to this parabola. For c equals minus 1 over 2, this numerator becomes 0, so we have y equals 0, that is the x-axis, always without the origin. For c different from 0 and different from minus 1/2, the level curves are parabolas with vertex the origin, but without the origin that always belongs to this parabola of the denominator, inside or outside the parabola y equals 2x squared. Some of these curves are represented in this picture, where also the excluded parabola, that is the points that are outside the domain, is represented. Observe in particular the two level curves c equals 0, that is the y-axis, and c equals minus 1/2, that is the x-axis, always without the origin. Consider the function x squared plus y squared over x plus y. The domain is x plus y different from 0 coming from the denominator, that is all the points of the plane except the line x plus y equals 0, that is the bisector of the second and fourth quadrant. The level curves are given by the usual equation x squared plus y squared over x plus y equals c. This is empty if c is 0, because if c is 0, the equation x squared plus y squared over x plus y equals 0 is only satisfied when x squared plus y squared is 0, that is the origin that does not belong to the domain. If c is different from 0, we have this equation, that is the equation of a circle with the center, the point c over 2, c over 2, and passing through the origin because there is no constant, without the origin itself that does not belong to the domain. All the centers lie on the line y equals x, that is the bisector of the first and third quadrant, and it is perpendicular to the excluded line. Some of these level curves are plotted in this picture together with the excluded line. Consider the function x plus y e to minus x. In this case, the domain is all the Cartesian plane. We have no condition, and the level curves are obtained by this equation, that the usual equation. This can be rewritten in this way. If c is 0, we obtain a line y equals minus x. If c is different from 0, we need to sketch the graphs of the functions gx equals gx, ge to x minus x. We've computed the first derivative, that is very simple. C prime g prime x is c e to x minus 1. If c is negative, this expression is always strictly negative, so we have decreasing functions. If c is positive, we have functions that are decreasing and then increasing. So we have a global minimizer in x equals ln 1 over c. Also, the second derivative is immediate. It is c e to the x, so the functions are concave for c negative and convex for c positive. Also the limits can be easily computed. The limit that x tending to plus infinity is minus infinity if c is negative, plus infinity if c is positive, while the limit at minus infinity is always plus infinity. The following picture shows some of the level curves. As said before, when c is 1 or 2, that is for positive values, we have a global minimizer, and here a global minimum, otherwise decreasing functions. Consider now the function x plus y over x squared plus y squared minus 1. The domain is given by this condition that comes from the denominator. So the domain is all points of the plane except points of the circle with center the origin and radius 1. The level curves defined by the usual equation are x plus y equals 0 if c is 0. X plus y equals cx squared plus cy squared minus 1. If c is different from 0, this can be rewritten in this way. So when c is 0, we have a straight line without the points of the circle x squared plus y squared minus 1 equals 0. If c is different from 0, the level curves are circles with this center and this radius, always without the points on the circle x squared plus y squared minus 1 equals 0. This picture shows some of these level curves. The level curve with c equals 0, this one, and some curves with c different from 0. This is the excluded circle, that is where the denominator of the fraction is 0. Consider now the function fxy equals square root of xy. The domain is xy greater than or equal to 0, that is the first and third quadrant. In the Cartesian system, we need both x and y positive or x and y negative in order to have the product positive. The level curves are defined by the usual condition. So if c is 0, x equals 0 or y equals 0, that is the pair of the Cartesian axis. If c is greater than 0, xy equals c squared. If c is negative, we have no level curve. Xy equals c squared are hyperbolas of the first and third quadrant. Some of the level curves are pictured in this picture, are plotted in this picture. And observe when c is 0, the two axes. As a final example of this collection of exercises, consider the function x cubed minus y over x squared plus y. The domain is x squared plus y different from 0, coming from the denominator of the fraction, that is all the points of the Cartesian plane except the parabola y equals minus x squared. To obtain the level curves, we use the traditional equation that can be rewritten in this way. Now we must distinguish two situations. If c is minus 1, we obtain 0 equals x cubed plus x squared, that is x squared times x plus 1 equals 0. So the level curve is the pair of vertical lines x equals 1 and x equals minus 1, obviously with the exclusion of the points belonging to this parabola, that is the points where the denominator is 0. If c is different from minus 1, we can rewrite this equation in this way, x cubed minus cx squared over c plus 1. We need to sketch the graphs of these curves in order to have a clear idea of the characteristics of these curves. We computed the derivative, that is very simple, and the sign of this derivative depends on c plus 1 and on c. The sign depends on the value of c. we consider these cases: c greater than 0, c equals 0, c between -1 and 0, c less than -1. We have excluded c equals -1 because in the case c equals -1, we already know that the level curve is a pair of vertical lines. We consider the sign of the two factors that are in the first derivative, this and this. The signs are represented here. This is a straightforward calculation. There is no need to make observations. They are straightforward. And we obtain the following picture where we have represented some of the curves beginning with c equals -1 when we have the two vertical lines x equals -1 and x equals 0, with the exclusion of the points that intersect these two lines with the parabola that makes the denominator equal to 0. Then some curves for c equals 2, 0, -0.8 and -1.5, with the characteristics represented by these signs of the derivative. In these cases, for instance, we have a maximum here, a minimum here. Here no maximum nor minimum. It is the function y equals x cubed. In this case a maximum and a minimum. In this case a minimum and then a maximum. And this is exactly what happens in these pictures. Sometimes before a maximum, a minimum and then a maximum, sometimes before a maximum and then a minimum. Obviously that we must exclude the points in the belonging to the parabola that makes the denominator equal to 0. This concludes this collection of exercises on level curves.